We're rolling here.
This meeting is being recorded.
Okay. Well, welcome everybody to the first meeting of the Seattle Robotics Society in 2023. Glad that there's plenty of you here. Hopefully, probably be more of you showing up here as the time carries on. Just in case you're wondering about this background behind me, I shot that from my front porch about an hour ago. So that's the view I have from my house here in Idaho. So we are loving it. I'm going to show you something. Some of you may even recognize what I'm going to show you here shortly. So I'll get going with the agenda here. You know, usual agenda. Follow this. Yeah, pretty much. Yeah, look, I think pretty close. If you are not actively speaking, please mute your microphones so that we can kind of stay focused here. And if you do need to, you need to share something, of course, don't be afraid to do that. Let's see. I will start off with the in-person meetings in the first facility. So I finally got a response from Eric Van Buren, who is the field house manager at their facility in Kent. And it's looking like we may be able to get something going. Now, there's some logistical stuff we have to figure out, because since I am no longer live there, so I can't run these meetings anymore, at least not in person. I potentially could do it via Zoom, be your virtual host. And we are planning to continue to have the basically do them hybrid. So those of you that are not Puget Sounders can still participate, or if you've lived way out on the peninsula like Richard does. So anyway, we are potentially looking at probably toward mid-year getting something rolling again. It's just a matter of kind of getting our logistics going, and they are in the midst of getting ready for the next first season. So the facility wouldn't be available for several months anyway. So we'll update the website when we have some more specific details about what's going to happen with that. So as I mentioned a little bit ago, my wife and I have moved to Idaho, and we're pretty much settled in. We are in Caldwell, which is about a half an hour west of Boise, and it's about 66,000 people live here. So it's not a tiny place, but it's not a huge place. But it's very nice. We really love it. And I'm planning to continue to do these meetings online and do the meeting preps and the website and all that kind of stuff as before. But somebody local, Lloyd, hint, hint, will probably end up being the guy. But he could always use help. So please avail yourself. I'm sure he would greatly appreciate that.
Help me! Help!
So here's my quiz of the month. Does anybody recognize these things?
I want to say they're the vertebra of something.
Stepping on one feels like it.
Oh, are those like Calthrop stickers?
They are something like that. You're actually very close there, Terry.
Okay, let me. Survivalists make by welding two nails together and then bending the nails in different directions to make a pipe for the tires.
Try that. Have anybody ever heard of those?
Oh, you know what? I have heard of those because my wife is from that area, and she has told me about stepping on those.
Oh yeah.
Yeah.
They are literally like bone in terms of how hard they are. They don't crush. They basically, you step on one of these things and you know it. And you can see from my size comparison, they're very tiny. They tend to get tracked all over the place. They stick to the bottom of your shoes or the bottom of your feet. And so it's a very common practice to remove your shoes when you enter a home here in Idaho because of these little guys. And this was one I just found on my floor this morning. So it's 25 degrees out right now. It's snow on the ground, but these things are still around. So
and by found it, do you mean that you found it with your foot and then pulled it out of your skin afterwards?
you know, I don't, let's see, how did I think I stepped on something near it and I looked down and then I saw this thing and picked it up and I think, oh, that's one of those. No, I did not find it with my foot, fortunately.
What fundamentally is it? Is it a seed or is it
I haven't done the specific research. I think it may be, yeah, it's some kind of a little thing that attaches it, or it's part of the plant, and then I guess it spreads itself by clinging to things. And so what's really fun is, of course, if you own a dog or a cat around here, they can pick these things up pretty easily.
Yeah.
And they're can be rather painful for the animals. So
wait, Steve, are we talking about a new form of robotics here, where we make something with little copper wires that stick up from the ground and people walk around? Is that is this the new plan for a distributed Wi-Fi network?
Well, it could be. I personally, I'd like a machine that could just kill these things. I understand these plants are very, very difficult to kill. They can be, but they use really nasty pesticides to do it.
There's a link to it is.
Okay, throw something in there. Thank you. Yeah. Okay. Oh, it looks like yeah. Okay. Thanks, Lloyd. So anyway, sorry for the little diversion there, but I hope it was kind of entertaining for you.
Interesting, and should I ever get to Idaho, will probably save my feet.
Yeah.
It's highly recommended to always wear something with a sole here. Don't walk around in bare feet. Okay,
saving our soul.
Yeah, something like that. Yeah, it's kind of a sort of a religious experience of sorts, I guess.
I'm absolutely certain that the Lord's name is definitely involved in the religious practice there, right?
I'm pretty sure it is, and you definitely hear some, you hear plenty of expletives when people step on these things. One of the things that I was reviewing the email that I got from Eric Van Buren regarding the facilities there, and one of the cool things that they have done is that they've built a portable video cart. So they have a cart that has a screen, computer, and basically, and then a Wi-Fi connectivity and all of that built into it, and they move it around. They use it in their office when they're doing smaller meetings. The office area is much smaller than in this facility than it was in the previous facility. So it's not going to be feasible to meet in there, unfortunately. So you're going to end up being out in the high bay of the warehouse, and you got the gas heater that's up there, the ceiling, and then remember how noisy those things can be, and there's going to be times of the year when it's not going to be super comfortable out there. But it is what it is, and the price is right. But this cart is very portable and easily moved. So the plan would be then to just basically move it out into the high bay area near where we could set up chairs and tables and things like that. And then so shouldn't be too big of a deal to get the meeting set up. Probably a lot less setup than what I was doing, because I was doing all of that myself, bringing all my own equipment except for the projector, so anyway, let's see here. Oh yeah, and I will mention this again. I had kind of hoped that I would be able to start a kids class here this week. Don't have any kids at this point, so I don't have anything definite set up yet, but if there's somebody out there, if you've got a kid in the 10 to 13-year-old age range that you think would be interested in doing a virtual robotics class, feel free to connect with me through this Mr. Steve's Robotics Club at Gmail, and I will and I'll reach out. their classes it's a 6 weeks, 6 session, approximately an hour a week, runs about, I'm not sure about pricing. It's in the $150, $160 range is about what I'm charging for the full 6 weeks. So, and then the kids would have to, their parents would then need to buy the kit to go, which is about $150 as well. So it's about a $300-ish experience that over 6 weeks. Oh yeah. Robert, I saw that, I saw that email and I had not had a chance to look at that yet. So Robert sent me a bunch of really cool things that I got to check into, a bunch of new potential presenters. And so I will get on that. Let's see. I don't have any specific events. I don't know if anybody has anything to mention. I know the folks at Snowco Makers, Makerspace, they meet, let's see, I think it's second
First.
Saturday of the month.
First Saturday of the month.
First Saturday of the month. Okay. And so it's compatible with our meetings. So, you can join those guys if you want. And they're always doing cool and interesting things up there. So.
And it is a hybrid meeting experience as well. So they
Yes.
do have
Okay.
they do also meet on Zoom, and that is on their meetup page whenever yeah.
Okay.
Okay. So that's where that's at.
Cool. Okay. Thanks, Donna.
I do have something to share there. I don't know if I came in a little bit late, so I don't know if you already mentioned this, but they have scheduled a PopCan challenge in May in the Seattle Center.
Let's see. Do you know about that, Lloyd?
Yeah, actually, we've been talking about it at our meetings. We were talking about attending it, but that was kind of not working super well. But yeah, we are aware of that one.
Okay.
Cool. Okay.
Yeah, that's Saturday, May 6th at noon.
Saturday, May 6th. Okay. I will add that to my my list of notes here. Let's see.
In the exhibition hall, which is the exhibition hall is a different building, isn't it? Than
Yes.
the armory.
Yeah.
Yeah.
Yep.
Right. That's on it's actually up on Mercer on the north side of the campus. So
yeah. That's out on our meetup announcements too. So if you go to the meetup for Snowco Makers, you should find that as an upcoming event.
cool. Okay.
I also wanted to mention, hi, this is Musa, and this is the first time I'm joining this meeting. Can you hear me all right?
Yes.
Yeah.
Yes. So we have, so in Renton, we started a robotics workshop for kids aged 9 to 14. And we will have like a demo session sometime later next month, maybe mid-Feb. So we're done with all the instruction classes. We are right now in the task sessions of this. And so we will have something mid-Feb. That's mostly like demo sessions from all the kids' projects. So.
Do you have a link for information about that?
We don't have a website, so we just started like last month. But I can set something up. So we have like 15 kids and like around 6 mentors and one instructor who's like from Microsoft, principal engineer. So so that's what we've been. So I'm also like from Microsoft. I'm a engineering manager there, and this is more like a non-profit organization sort of thing connected to a mosque community. And so yeah, I can share more details. This is my first time here, so I just saw that event's coming. So we have an event coming next month, so I can share more details in the next month.
So let me see. Oops, I'm gonna let's see here. So you can our club email. Oh,
I'm sorry.
Our club email there at Seattle Robotics Society at Gmail. So if you could send me something, I can get that onto our website.
Awesome. I will do that. I sent an email. I don't know if I got a reply to that. I did send an email like 4 weeks ago or so.
Yeah, I'm not the, sometimes it's like, oh, is it, I don't go there every day, or I go there, try to go there a couple times a week, and sometimes it's like, oh, I think I've been there this week, but then again, maybe I haven't. So
Okay.
when you have 3 or 4 or 5 different emails, it's kind of like, how many of these things can I actually keep up with?
Yes. You can get busy.
Yeah. Okay. Okay. So anyway, that'd be great, and we'd be happy to post information about that, and obviously anything you want us to put someplace, where people can see it from our website, just send me something there. And I can't promise that it'll be instant, but I'll try to get to it as quick as I can. So send
Thank
me.
you. Thank you so much.
Yeah, thank you for sharing. That sounds like fun. Okay,
Yes,
well, I'm gonna turn it over to Lloyd here for a moment and have him just kind of give us a Robothon update. And
Yeah, so we've got 2 events planned for this year. The first one will be June 10th, and that is going to be a Robothon exhibition. That'll be an online only event, just like we generally have been doing for the last couple of years. So we'll have between 6 and 8 presenters just presenting whatever you would like. And that'll go for about 2 to 3 hours, depending on how many presenters we have. Yeah, we haven't locked the times down yet, but Donna, I think we'll probably do like 12 to 3 like we've done in the past.
Probably, yeah. For
It'll
start, start. We can plan on starting at noon. So
yeah, well, something like that. So pretty much the same thing we've done. The second event will be August 9th, and that will be a Robo-Magellan run. That will be an in-person event. And again, Donna, do you remember the name of the school?
Oh, you betcha I do. It's
Okay.
Sunnycrest Elementary School, and that's a great campus area for Robo-Magellan. I'm sorry, Lloyd, if I take over here for just a second.
Go for it.
But it's going to be an event, as Lloyd was talking about, where we're going to have a different venue this time for our first in-person event in about 3 years or so. And it's going to be at Sunnycrest Elementary School. We are literally just going to be outdoors for this entire time. And we plan on hosting the Robo-Magellan proper contest itself. It's going to be an open registration and accessibility for that. We also plan on hosting a couple of other smaller scale, less technical required challenge level type contest as well. For instance, maybe mini sumo or line maze, that type of scenario for 2 other potential contests to run on the same day. We have not nailed down an exact time block frame yet. We are still, Lloyd and I are working the details to actually reserve our target date and set a time and get everything worked out with the school for all outdoor access. So back to you, Lloyd.
Yeah, so thanks, Donna. I think the 2 big things there are, one, if you have a Robo-Magellan robot and you would like to, and you haven't run it in a couple of years, start getting it ready. And I guess the second ask is if you have a strong feeling on which additional contests you would like us to run, mini sumo, line maze, line following, any of, whichever of that, let us know, because I think we're pretty open to that, and it's kind of dependent on what people want to do. So yeah, anyway, so first one is June 10th, second one's August 9th. Little time to get things ready. Okay, thanks, Steve.
all right, I was just gonna throw those. Let's see, did it do it? Come on. Scroll down here a little bit. Come on, let me in there. There we go. All right. Okay, and let's see. There will be information on both of these available on the robothon.org website.
Yes,
So,
yeah, that is coming. I don't have that detail up there yet.
Okay. And of course the sessions will be recorded. They'll be posted on YouTube, on our YouTube channel. So you can watch them live or you can watch them post live. So is that dead? Post event. All right. Okay, and I will maybe I'll throw some. I'll tweak this slide a little bit too here for next month with some more accurate information on it. Come on, there we go. Okay, and okay, so it's actually June. I have May in here, so that was an update. Okay, and presenters. I don't know whether to ask people to send me more stuff right now or not. Robert just keeps feeding me like tons of stuff. I've got plenty of follow-up to do. So I guess I'm going to say at this point, we're good. We're booked all the way out through July. So that's cool. So I'm very pleased that we've been able to fill our calendar up. So if I can find people willing to commit, I think it'd be pretty easy to get all the way to the end of this year. So it's awesome. And of course there's well, let's see. I was gonna throw. I'll jump in here first. So a little bit later. Just a little bit later, Donna Smith is going to share with us a presentation she calls Finite State Machines Demystified for Robotics. So that is coming up. And I just, I make these slides up. I go out and I just look for images and stuff, and I kind of make these things up. But I mean, I was starting to read a little bit about this like, this is going to be a cool presentation. So I'm really looking forward to it, Donna. So thank you for doing this for us.
Thank you, Steve.
Yeah, and so this will be coming up. We're going to take I'm planning for us to have just a very short break because I always usually need one about mid-meeting for, I'm getting to be that age. So open discussions. So this is going to be interesting. So I keep throwing this up here every month, but it's kind of like, we got presentations lined up for like way out there. But it was mentioned during the pre-meeting discussions here that we should have a talk about the Chat GPT, and I'm open to that. My son has been talking to me about this, and Richard and let's see, I don't remember, and Lloyd, and talking about how this is pretty extraordinary piece of AI, and we really should have a discussion about this, So I'm open to anybody that would be interested in hosting that, leading that, facilitating that during our discussion time. That would be very cool.
Steve, I'll totally sign up to facilitate and lead that discussion. That's
okay. Thanks, Lloyd.
I'm diving into.
What we might do is maybe make that a kind of a pre-presentation sort of a thing too. I don't know. It's like, I want to kind of shoehorn it in there somewhere. I'm not really sure how to do that. Sometimes it's like there's so many good things that we could do. We only have so much time, So okay, so so I'll keep that in mind, and try to kind of think about how we could do that, because it's a fascinating piece of software. So we could have continue discussions after the meeting. Of course, that's an option too, but people can't necessarily hang around. You've already been here for 2.5 hour meeting, and then to continue on. I know some of you could sit here all day and talk about robotics, but we want to try to keep it, from getting too lengthy. You know what I mean? So, but anyway, we do have opportunity to just have general discussions about robotics after the meeting, and shut the recording off at that point, and then we can just kind of continue for however long you want to chat. So, okay. Okay, so it's about 11, almost 10:30 your time. So we are kind of at a good place of being able to go kind of around the room. And at this point, I want to open it up to anybody who's got something that they would like to share. If not, I have a couple of kind of ticklers here that I can throw out there to get maybe get a little discussion going. But I'd like to have let you guys go ahead and start. Anybody got anything that's just been burning in their bosom here all month and gotta get it out? Of course, we could have our discussion about Chat GPT, but then we might run right over the top of Donna's presentation.
So Steve, just a quick note here. I just logged in and put your goat head thing into Chat GPT. I'll post its response in the chat just for fun.
Oh, I love it. I love it.
Then you'll have what you got from the web and what you've got from Chat GPT.
That's cool.
I have a yes for you at some point here, Steve. There were, for the first time, I'd say an entire floor of robots there.
Yeah. Okay. I'm gonna.
So I had
took the share. Oh, go ahead, James.
Oh, I was just gonna say I had a fun little adventure the other day. Went back to the company headquarters, and then one of the other guys and I flew out to Phoenix, Arizona, and rode around all day in the Waymo cars, which was really, really, really interesting. The two-line short version of it was very, very good, but not perfect. The friend that I was with said that he felt safer in the Waymo car than he did in his Uber on the way home. And I felt a little bit safer with my Lyft driver on the way home from the airport than I did in the Waymo car, but not by a lot. It made a couple of interesting mistakes, nothing life-threatening, but in general, it was extremely authoritative and confident, and it did, like 99.9% exactly the right thing. So generally impressive. I'll post a link to I have a what do you call it? A Google photo album with a bunch of little, pictures and videos and stuff like that. And you'll get to hear my coworker scream at least once, which was a lot of fun. And some of the videos, basically I was taking them right after something had happened. So I'll be like describing like, oh, well, this happened. And I wasn't filming it. So some of it's a little boring and dumb, but some of it is actually kind of interesting. There is one clip where you get to see us come within inches of hitting a car in front of us. And about 5 minutes after that happened, they called us on the car phone. There's the service people are monitoring all the time. And they called us and they said, hey, everything's fine, but at your next stop, we'd like you to get out and you can call another car, but we want to bring this car in for servicing.
That's disturbing.
Yeah, it was kind of a, my butt started making diamonds right about that point. But honestly, overall, very, very, very good. At least as safe as a human driver, if not more safe. And I think the key point is, I really do think that the combination of like a level 3 system with a human driver is like much, much safer than either one of those two alone. So I should have titled that, because like the bare link, people aren't going to understand what that is. I'll post it again with a title.
Okay, thank you. It seems like what comes to mind about the self-driving cars and that whole thing, and I think we may have had that come up in we've had a couple of facilitated chats on the topic. But, when things are pretty, the situations are pretty benign, pretty ordinary, nothing too extraordinary is happening, it seems like they do pretty well. And what I'm always what concerns me is those fringe cases, or those extreme situations. You're driving along and something comes out in front of you unexpectedly. How quick does the car respond to those kinds of things, and how well does it respond?
Well, actually, although I missed filming it, there is an absolutely brilliant example of that during our adventures. I described it in one of the videos, but basically we were following a pickup truck, and those thin foam sheets that they put like between pieces of wood and when they ship IKEA or something like that. You know what I'm talking about? It's like that packing foam stuff. One of those blew out of the bed of the truck in front of us, and the car just considered it, as it should have, considered it to be a solid object floating through the air towards us, and totally slammed on the brakes and pulled to the left and was like, because this piece of foam was being kind of gently blown along the ground, right? And it was like, oh God, what's that? Oh geez, stay away from me, get away, kind of the car was like reacting to it. And we did have a case of somebody pulling out in front of us. The car, did a great job of avoiding it, both braking and pulling to the left into the oncoming lane, but there was nobody oncoming, right? So it was absolutely the right thing to do. So I think you're right, but I think a lot of those kind of things, it still will handle, really, really well, right?
You're right.
So it'll be interesting to see, especially in light of the full self-driving. I guess the Tesla car didn't really cause the accident, but it changed lanes into the into the fast lane, and then immediately started braking. And then when the cars behind it slammed on the brakes, they caused a pileup. So yeah, that's another example of humans like not, doing as good a job as the car would have done. Because if those had been robot-driven cars behind there, they probably wouldn't have had a pileup. But humans tend to tailgate, and and then when a robot car does something unexpected, they all have a crash.
Right. And the advantage that the car has is complete situational awareness. I mean, except for the unexpected thing, of course, but the car knows what's on both sides of it. It knows what's behind it. It knows how, if that car behind it is like right on his tail, it would know better probably than to slam on the brakes, because that would of course cause that car to, come straight into the trunk. So it can take the full, it takes in all of that information. And human drivers, a good human driver, of course, would sort of be in this constant scanning mode as well. You're constantly looking at your mirrors, you're looking in your rear view, you're looking to the left and right, and you're making sure that whether there's somebody back there on your left rear tail that if you go to the left, you're gonna cut him off and probably cause more accidents behind you. But maybe there's nobody on your right. So therefore, if you got to swerve, you can swerve to the right, and there's a better chance that you're not going to hit something. But how many people drive that way? I
was about to say a good human driver is what you said. How many?
Yeah. Oh yeah. I qualified that.
Yeah. I think the other thing that was interesting to me was that the car was far more aware of the environment around us than we were. Like, it knew every single car that was coming, every single pedestrians. And the other thing that was interesting, and you'll see this in the videos too, was it was scanning constantly, and then it would like decorate things. Like, it would draw a rectangle where it saw a car, it would draw a circle where it saw a human, right? And then it would highlight the ones that it was concerned about. So like the car in front of you quite often had a little green rectangle underneath the gray rectangle that represented the car. And if a human was on the sidewalk, it was just a gray circle. But if the human walked into the road, suddenly it had a green highlight underneath it, right? And the coolest thing that I saw the whole thing, I'm sorry I'm chatting so much about this, but it was exciting.
No, this is great.
The thing that I enjoyed the most about it was, this is something that I've been talking about in teleoperation and in doing problem solving with things like strips and stuff like that, is you have to have a high semantic representation of the world around you. So it's this taking a point cloud from a 3D scan, which is just god tons of information but no knowledge, right? And then translating it into a rectangle, which is knowledge about what that set of point clouds represents, right? So we were coming along, and I this, if there's one thing I wish I had filmed, it was this. We were driving down the street and we saw a car, and there was a parked on the side, and there was a woman opening the back door on the street side of the car and taking stuff out. So she was opening the driver's side door on the back while the car was parked, and our car highlighted the vehicle, the parked vehicle, as a rectangle. And then from the left side of the rectangle, you could see this little point cloud of green blops that were out there, basically saying, well, everything else in this point cloud tells me that this is a vehicle, but it's going like, what is this little green, what is this door that's sticking out? Like, cars don't have things sticking out from them. What is this, right? So that was what the car was, like, quote, thinking, end quote, right? Mm-hmm. So what it was doing is it had seen the point cloud, made a higher level semantic representation of that with the rectangle, and then compared the rectangle with the point cloud and saw that there was still a difference, right? This door doesn't match this higher level representation, right? And so it slowed down, pulled to the left, kind of eased by, which is exactly what it should have done. But it was brilliant to see that what it was doing was, that whole thing of taking the low level information, building into a high level set of information, and then comparing that high level set with the low level set again to see, like, well, what's the difference between you? How is my model of the world wrong, right? I just thought it was just great.
That sounds, that's pretty amazing. That's and there's there's like an infinite number of possibilities, really. So that's pretty remarkable that it was able to do that well.
Yeah. Also, there's a podcast that I'll track down and link to, where what's the name of the guy? Malcolm Gladwell. He loves Waymo, and he did the same thing and went and rode around in Waymo cars, and they got a beach ball and kind of pushed to roll the beach ball out in front of the Waymo car just to watch it react. The car with one guy in the car and Malcolm outside, and then Malcolm, being a fool, got out there and ran in front of the car as it was driving, and then kind of chased it around. And the car was rerouting in the parking lot, trying to get away from him. And he's running and trying to catch up with the car and get in front of it again. Anyway, so, I'm sure at some point in time, the Waymo people are going, oh man, if that wasn't Malcolm Gladwell, we'd be canceling his account. What is this idiot doing? Anyway.
Awesome.
So the things that it didn't do well is, like I said, it almost hit another car. It came very close. It won't park, literally will not park. Every time it stopped, it just kind of, like one time it literally just stopped in the middle of the street and said, "You're at your destination. Please watch for traffic as you exit the vehicle." There's another time where it waited for a car to come out of a parking space and then didn't take the parking space. I mean, it just kind of sidled up and blocked 3 spaces in order to let us out. So I don't know what the deal is with that, but they don't park. It would not take the freeway. We tried multiple times to get it to take the freeway. It would not go on the freeway. Never went over 40 miles an hour. So that was, most of the trip was 35 miles an hour. And it would take routes, if you wanted to go at 2 catty corner points on a city map, normally a human will like take the main street horizontally and then take the next turn right and take the next main street vertically in order to get to the other point. You know what I'm saying? It would try to draw a straight line between the 2 points. And so it would route through like all these tiny side streets, alleyways. It had us going. And if it was a human driver, I would have said it was just running up the ticket or running up the time meter. But so little things like that, but in general, very good. All right, I should stop talking. Oh yeah, thanks for the link. Malcolm Gladwell takes a ride in the coolest car ever made. That's the one.
Yeah.
That's a good
okay.
one.
Yeah, that. Yeah, it's like routing directions in Google Maps too. You know, sometimes it's just like this is. You know, you I found myself going, what in the world is it doing? I mean, and you know, yeah, because you know, we build mental maps of where we live. You know, we have a general feel for where things are. We don't know exact data. Like we can't say it's, you know, 12.53 miles from where I am to where I want to go. You know, we don't have that kind of information in our heads, but we do have a general idea of direction, and we know kind of how, you know, how you can get from here to there. And I guess we kind of tend to expect that, you know, the routing software to follow something that makes sense to us, but sometimes it just comes up with the craziest. And that zigzaggy thing, I have definitely been on that before there, where you're sitting there zigzagging through neighborhoods. You know, you go up 2 blocks and then you go 90 degrees 2 blocks, and then you go 2 more blocks, and then, you know, and it's like, wait a second, there's a main arterial about a half a mile down the road that'll completely bypass this whole area in a quarter of the time that this zigzagging thing is going to take. And then you just ignore you ignore the guidance, and you just do what you want. You know, you do what you know is the right thing to do. So it'll get there one of these days, though. Anybody else?
I have a bunch of photos to share for you at some point from CES.
Daddy.
Well, why don't you go ahead and start. What I'd like to do, Richard, is like to wrap things up about 5 to 11. So
I'm on the wrong device right now, so I'll stick around after the meeting, and maybe I can get some put together for that. But I need to get a different device out first.
Okay. Anybody else? So I want to make the mid-meeting break pretty short. Donna's got enough. She may go a little bit long because it's a fairly big topic. So we want to try to get her going pretty close to 11. Anybody else got anything? Let's see. Just kind of looking to see if I've got any other notes here of stuff. Well, don't all talk at once. Yeah, I see that. I didn't see. Let's see. I don't think Greg is online this month. There, give us an update on his arm. No. Let's see here. Okay.
Hey, RJ, or RJK? I don't know what your first name is. I'm sorry.
That's Robert Kellogg.
Robert. So you posted something there about RDP113, awesome robotics company with no ROS. I'm curious if there's a movement called no ROS, like no SQL. I just want to join up and promote that movement if it's possible, but or is that just a typo? Oh, okay, no worries.
Okay. Let's see. All right. Well, maybe I will maybe I will try. Let's see here. Okay, I am going to try and see this will work. Chrome tab, share audio.
All we're doing is we're carrying out beekeeping just like a beekeeper would do in the field, except we're using robotic hands and computer vision and cameras.
Come on. So, whoops, sorry. You know how these darn YouTube videos, one after the other, and then especially these crazy things that come out of Japan and China and the Far East. They usually always get some really kind of crazy things. But robotic beekeeping, and I know there's been, it's kind of something we don't really think about is, these little bugs are kind of, they're critical part of the Earth's ecosystem, and the pollination of flowers and plants, and that that it's very important that all this stuff continue, or it could be bad for us. Mm-hmm. So it's kind
one of the folks in the Snowco Makerspace, Kelly, he actually had a beehive with a wireless camera in it to monitor his beehive. And there's, I think there's instructions out on Instructables on how to actually make a bee cam where you can monitor your hive's health and functioning. And Kelly was not just monitoring with a camera; he had temperature and humidity and something else that he was monitoring.
Yeah, that makes that sounds like that makes a lot of sense to do that. Keep an eye on the health of the hive as well as the bees, and yeah. Let's see. Okay. Anybody else? We've got a few minutes yet here. If not, I'm going to go ahead and we'll just start our break. And oh, Mohammed, you have something to share there? You just unmute yourself.
I have unmuted myself. I don't know if you can hear me.
It sounds like you're a long ways from the mic.
Yeah.
Is this better? Hello?
Somewhat. Yeah, it's
better.
Oh, that much better. There you go.
Sorry, yeah, that is basically me using my laptop in whatever clamshell mode. So yeah, so I had some questions. So we in the robotics workshop are using the Lego Mindstorm kit. I don't know if people are familiar with it. That's so. Does anyone know of a good resource for good projects to build on top of the Lego Mindstorm? Spike,
Anybody?
Prime kit, something.
Doesn't the there's 3 different levels of FIRST Robotics.
Uh-huh.
On the lowest level, I believe also uses the Mindstorm. I shouldn't say the lowest level. The entry level, the one that's targeted towards the youngest kids. And I think they publish a lot of the information about their prior challenges. And then if you contact individual teams, some of those have shared their code and what they've done. You could watch their videos and see what they've done and try to recreate it. So that might be a resource for you. The other one is there is a subgroup on Hackaday.io. There's a group there, which is a subgroup for the Mindstorm stuff. So if you go to Hackaday.io and then you search for it, you'll find some interesting, strange things. A certain percentage of those will be people who have taken the Mindstorm stuff and made extensions to it, or who have changed the way it works, or who have, hacked it in some way. But there's also some interesting stuff.
Awesome. So we have a few projects that we want to productionize. Does anyone have experience with productionizing a Mindstorm project to maybe, I don't know, using a 3D printer to scale it to maybe 100, 200 pieces and, start selling them? Has anyone on this forum done something like that? So basically we have a prototype built using the kit's components, right? And we know that it works. It's sort of like a POC. Now we can print it with a 3D printer, right? At probably much less the cost. The kit costs $500. We can't sell anything with that. But if we can do something smaller with smaller components that are like custom built for it, and we can scale that production and sell those kits in wherever we want to sell them, something like 100, 200. Does anyone have experience with something, or maybe some Chinese warehouse vendor who can do that productionization? Anyone done that before?
The route I took was trying to produce the stuff myself, and then having China stuff in and copy it and flood the market and kill my business. But maybe if you go and pay China up front, then maybe they won't compete with themselves. I don't know.
What is it? Key China? Huh?
Yeah.
What did you mention? Key China?
I'm sorry. I said I made an electronics products, a series of electronics products, and I produced them myself in the U.S. here, right? And I sold them in the U.S. marketplace. And then people from China, manufacturers from China, noticed that they were gaining popularity and produced their own knockoff versions, which I was unable to stop. And then they put my business out of business. So maybe going to China and paying them is a smart idea, because then hopefully they won't compete with themselves.
Yes. It's essentially it's like the economies of scale, right? They do that faster at a lower cost. So
exactly. They do it. I won't say better, but they do it at a lower cost than we do. So quality control can be, an issue. But maybe if you're paying them, then you can get some quality control in there as well.
Yes.
So,
a good quality thing that lasts a year or two, depending on what kind of thing you're building. So
I do have one friend who went that route. He needed to produce a great number of a particular product. It was
Uh-huh.
a self-charging flashlight, and he went and contracted with China. They sent him prototypes, which did not match his spec. So he ended up actually traveling to China and meeting in person with the people.
Yeah.
He found that there was a lot of just like they would say yes and then not do what he said. But if he went there and actually, guided it directly, then
Mhm.
he had better luck with it. But that was, 7 years ago. So I don't
Yeah.
know. Things have changed, but pre-pandemic, and now things have changed again
Yes.
with the
Yes.
pandemic. So I don't know what to tell you other than good luck
Yeah.
and welcome to hell.
Do you have a contact to share? So I've heard a similar story from a friend who's like run a tablet business of like selling maybe 2,000, 5,000 tablets, which he got built out of China. So it is a good model. I mean, he just got it built for a very small cost and sold it in the Middle East. So
Yeah. No,
so-
unfortunately, my contact has passed away. All us old guys were dropping like flies, so he's gone.
I mean, I still do
Sorry to
a fair amount of contract manufacturing and design that's produced in China and Vietnam. So if you want to hit me up, Mohammed, I'm happy to chat with you.
Sure. Yeah. If you can just put your email address or something like that on the chat, I can.
I'll be happy to do so.
Awesome. Thank you so much.
Okay, sure. So let's take about 5 minutes, and I'll get Donna going about 11:05, and you can see the time on the screen there. So I'm going to, I will be back, and feel free to do whatever you need to do right now, and we will resume in about 4.5 minutes. Hi, Donna. Why don't you, you're muted there.
Yeah.
Go ahead and get your, do you have your presentation up and ready to start?
I will here as soon as we're raring to go.
Why don't you go ahead and share it to the screen?
All right.
And I will stop sharing. There you go.
Oh, let's see.
It'll just, yeah. All right. Here's your desktop.
I'm witnessing the same problem that you did, Steve, with a slow load.
Yeah. I don't know if it's Zoom. I do these meetings on a Chromebook, so
right.
That may have something to do with it. But
right.
Well, that wasn't as slow as mine was this morning, though. So.
Well, no, I do everything local, so that is a big plus that way.
Yeah, that's probably part of it because I use I'm doing Google. My slides are on Google Drive, so they're in the cloud, and so it's got a. Yeah, I'm sure that that
has a bearing on it.
Yeah.
Okay. All right.
Okay. Well, let me just do a brief intro here, and then we'll turn you loose. So many of you have Donna Smith has been around the SRS for a long time and built lots of robots. She loves to compete in the competitions. Serves on the Robothon committee. Helps out leading meetings from time to time. So just she's a great resource here at the SRS. And so appreciate you stepping in here and doing a presentation for us. And with that, take it, Donna.
Okay, thank you. Thank you so much, Steve. Thank you so much for the great introduction. So today we are going to talk about, this is going to be a kind of an intro level beginner look at what finite state machines are, and specifically some of the programming methodologies, some theory, some vocabulary, and direct applicability on the robotics side of the house as far as building a basic finite state machine that is runnable on Arduino, specifically an Arduino Uno. And so that's the way that we are going to proceed today. Okay. All right. So Steve already took away a little bit of my thunder for my bio, but yes, I am a very long time member of the SRS, and I help with Steve, Lloyd, and others on the online and in-person robotics events and contests. So I'm an active member of the Robothon Planning Committee. I am also the newly appointed webmasteress for robothon.org. And I'm in the process right now of doing some revamping, re-engineering of that site. So that's something that we'll stay tuned for. And then some more about me. So I have about 15 years experience in the corporate engineer world. And I have 2 Bachelor of Science degrees locally here in Seattle from Seattle University. I have both an electrical engineering degree and computer science. And after my corporate engineering experience, I decided to launch my own businesses. And currently I have an online business called Your Tech and More. And I specialize in unique, custom built for individual as well as profit and nonprofit businesses of any size. I help to bring your technology needs to life, and by creating unique, cost-effective solutions and education to help facilitate your needs. So that's what I am currently doing on the on the business side. Okay, so some agenda points for today. So as I mentioned, we're going to be covering some basic theory, and to help answer, well, why are finite state machines so powerful, and especially for robotics, in the robotics community and robotics applications. We are going to talk about a specific finite state machine implementation that I created specific for this talk today using the Arduino Uno. I'm going to provide a video recording, pre-recorded, that I did prior to today of the actual demonstration walkthrough of my implementation. And then we're going to talk about my next steps for this project, what I have learned, and some anomalies that I have discovered. And then we're going to talk about some ways that you, as the audience member, can take these learnings and move on from there. And then we'll have an open mic Q&A discussion. Now I'm going to ask, because I've got so much to go through today, and to be more mindful of your time, I'm going to ask that you hold your questions and comments to the end. So please get out some kind of a notepad device. And as we go through things and you want to make comments or questions, please note them, and then we'll be able to open those up to you at the end. And also, you will have a downloadable set of materials, in addition, of course, to this recording of the meeting today. And I will be providing that shared URL link at the end of my presentation today for your perusal and consumption. Okay, so let's get on with the theory. Okay, so let's talk about a basic definition. So a finite state machine, or SFM, that you'll see frequently in the literature, basically has to do with an algorithm that has a finite state, or excuse me, a finite set of states and accompanying transitions to model any kind of a reactive system. Okay, that is the basic core definition. And this is a design technique that is very, very old. It is based on the traditional computer science topic of automaton theory, okay? And basically what happens is that a finite state machine is a design model, frequently for our purposes, developed and implemented in code, but it can also be implemented in hardware, as far as physical silicon on a board that handles your finite state machine implementation. But basically, it's a design model that's implemented as a set of states, transitions, and outputs. Outputs as far as moving from one state to another. In other words, the output is a new state, and it's great for modeling any kind of reactive system. So some vocabulary here. So let's talk about what a state is. And a state is a unique characteristic or output condition that helps to model what it is that you are developing this machine for, okay? And transitions are an input set, any kind of grouping of inputs that move from one state to another, okay? And finite state machines are developed from a set of system requirements. And I mentioned to do about the various inputs that comprise your system. Okay, and inputs are a set of sensors or timer ticks, timer counts, etc. Anything that helps to move the system from one state to the other. So those are some basic vocabulary elements that comprise a finite state machine model. And it's a very expandable design technique. Systems can employ multiple finite state machines, not just a single one like what we're focusing on today at the basic level. And it can be used with multiple types of architectures, either as raw code, okay, or with an RTOS or other operating system model that's can be used. And it applies either to embedded and robotic systems or in the generic programming systems modeling. It's especially popular in games development, okay? And using conceptually and in implementation, a finite state machine can really simplify your design and modularity of functions that are implemented, and it's a definite spaghetti code reducer, which basically reduces errors that can crop in. It's ideal for robotics because of the quick, high turn, highly reflective needs of a system. Okay. So now let's talk about down a layer deeper as far as common types of finite state machines. And again, this is taken directly from computer science, specifically automaton theory. And you'll frequently see in the literature, and also what we'll talk about today, there are two basic types. There's mealy machines, and then there's Moore machines. Now, a side note here, Moore machines are not a direct descendant from Lloyd Moore. Okay, so let's get that straight right now. Okay, so as far as the, I'm sorry, go ahead. What?
Oh, I just said thank you.
Oh, you're welcome, Lloyd. I just thought I'd add that. Okay, so the basic difference between those two types of machines is that it has to do like with the next state or the way that the overall look and feel of a machine is defined. So if the next state function is a function of both the current state that you're in and a set of inputs, that's what's termed as a mealy machine, okay? And also on the other side of the house, a state machine where the next state is a function of only the current state, that's called a Moore machine. So that's just some more vocabulary. I just wanted to let people know that whenever you go in and you start researching, learning more about finite state machines, you're going to see a lot of that mention of that vocabulary. But as far as the root implementations are concerned, and I just want that is not as, you really don't need to worry about that so much. I just wanted to get that vocabulary out of the way. All right. Now we're going to talk about some specific with designing these, some specific design steps at a basic level. Okay. And so you start with your system requirements. Again, this is all, it's kind of like OOP, object-oriented programming, where you have something that you want to model in software or in hardware at the circuit level, and you're developing a model. Finite state machines is something that can be viewed kind of as object-oriented programming as far as the modeling side of the house goes. So you're starting with your set of inputs and your set of requirements that your machine needs to adhere to, okay? And from that, you develop a pictorial diagram of your finite state machine design, okay? So that's going to be point one, all right? And then for our purposes, since we are interested in coding, not developing hardware for our finite state machine, then we move on from there to actually coding it, okay? And once your diagram is defined, your diagram is really is your first level milestone goal in developing a finite state machine. And because once your diagram is defined and you've got all your details in there that you need to move from one state to another, the overall architecture is pretty easy to create and develop, especially if you're looking at it in terms of a high level language such as C or C++, okay? Now, but of course, then beyond that, as far as beyond the architecture itself, whenever you're going in and coding the specific functions themselves for that execute a particular state, then things can get a little bit more hairy. That's where the harder part of the individual state coding can be more challenging. Okay. And as I mentioned before, you don't really need, for the practical side of developing what I'm going to show you here today, developing your finite state machine, you really don't need to worry about whether you're developing a Mealy machine or a Moore machine. That isn't, you just go with what you need to and move on from there. Okay, so now the next thing I wanted to show you is some basics for a C-level implementation. Oh, not that one, sorry. Okay, now, so can you see my new screen refresh there? Okay, okay, cool. All right. So this is going to be kind of a walkthrough. Let's see, I'm going to reduce this so I can move the screen around. Okay. Okay. I hope that's still viewable. So as I mentioned, this is going to be a review of basic C language implementation for a great way to design your overall architecture, taking your diagram that you create and then implementing it in C code. All right. Now, this particular model that is up here on the screen is a generic like PC model of, in other words, you're not on a microcontroller kind of thing. But this is something that's easily translatable into, say, Arduino or some other microcontroller. So you've got your basic function prototypes that you've defined, and you need to define a new data type. Again, now this is specific to C, okay, where you do a type def for a new enum where you're defining your set of states. Now for this particular implementation, we've just got states. We've got 3 states, A, B, and C. And so we are defining a new enum type with that declaration there. Okay, that's what this type def enum is. Then what we're doing is we're defining an array of pointers to a set of named functions. That's what the static void declaration is. So we're creating a state table that will quickly, on the fly, transition from one state to another, okay, in a simplistic, easy to implement, quick to implement fashion. So we're creating an array of pointers to named functions. I'm not going to go into the C lingo on all that. I'm just we are declaring that here. So for our state table, then we just got some typical global variables that we are defining, and we're defining them as static because the state or the information needs to be carried on from throughout the entire lifetime of the program. Therefore, they are static. Okay, and what's of the most importance here is this idea about the cur underscore state and the out variables. Okay, so both of these are going to reflect the upcoming state that we are transitioning to. Okay, and so out is an int because of what we have declared up here with our array of pointers to the functions, where we've got, and also the new data type. In C, everything starts at the number 0 and works up from there. And so state A is 0 in the array, and then B is 1 and C is 2. And so in this case, for this particular implementation, out can have a value either of 0, 1, or 2. Okay, because that's going to be what goes in for our next state. And then cur state is actually holds the pointer into functions A, B, or C, again, for the upcoming state. Okay, so enough on that. Okay, and so now we've got our traditional main while loop that loops forever. And so what we're doing here is we're initializing the state machine, and then we are going to loop forever, where we are continually calling, getting access to what the current next state is going to be. And in this particular implementation, because we are based on clock ticks to as one of the inputs into this machine, that's why we are implementing the clock variable, and we are waiting a fixed period of time so that everything has time to catch up and move the while loop along in a great fashion. Okay, so in other words, main that's one of the nice things about this implementation. It's very modular. You can easily add states as you go along, and not have to worry about munging things up, and for inducing errors that way. And also the main functionality, the main looping is so simple. That's one of the things that I like about this. Okay, and so then from there, then we're defining our individual functions. So we've got A, B, and C functions defined as individual void. So no returns in this case from any of these. And then we're also defining our initialize state machine function. Okay, so this initialize, let's start down here at the bottom. Initialize state machine function, that literally sets up the initial state for our machine. Okay, and in this case, for this implementation, state A is the initial state. So that's why we have the declarations and the settings as we do in initialized state machine. Okay, and then again, because this is a simplistic implementation, no great detail is involved per state. Okay, in this case, if we're in state A and a particular clock timer has elapsed and triggered, then we move from state A into state B. Okay, so that's what this is depicting here. If we're in state B, again, another advance of the clock has ensued and triggered. Then we move from state B to state C. And down here in state C, if another clock tick has been triggered, then we move from state C back to state A. Okay, so this is a real simple but extremely functional, simplistic way of implementing a state machine in C, whether we're talking about a PC implementation of some sort, and also transforms well in the microcontroller world. That's why I wanted to show this. That's why I showed it in such great detail. Okay. All right. So now let's go back. Okay. So now let's go back to the slides. Okay. So now we're going to talk about my state machine application that I developed, and what I decided to do, because one of my favorite SRS contests is Mini Sumo. Okay. And so I decided to create a robot simulation for the Mini Sumo, a Mini Sumo contest entry. Okay, so why did I choose a simulation, and why didn't I decide to build an actual finite state machine implementation of a physical robot? Well, I decided to do the simulation because I wanted to just concentrate on developing the methodology, being able to showcase the finite state machine itself, and not worry about all the physical sensors and all that kind of thing for this particular presentation. And the simulation is a great way to start your finite state machine development, or take your learnings of finite state machines to the next level. Try new techniques, employ additional finite state machines in your overall design, and or add in the use of a real-time operating system in with your implementations. So I would definitely recommend a simulation. I found it very, very useful. And so as far as a mini sumo robot design itself, I decided on mini sumo because it's a very simplistic set of requirements that a robot needs to adhere to. Conceptually, it's an easy robot to build your logic for. So that's why I went in the mini sumo direction. And specifically, the requirements of what a mini sumo robot is basically 4 requirements. It needs to stay on the ring or on the Dehodo itself, the competition ring, as it's running around and doing it during a contest. So stay on the ring. That's requirement 1. Requirement 2 is hunt for your opponent. Okay. Number 3, target and aim at your opponent. And number 4, be able to actually attack your opponent and hopefully be able to extract that opponent out of the ring. Okay, so those are the requirements of a mini sumo. And so with all that, the states that we're going to talk about in detail are I think very intuitive, and I think that you will see that as well as we go through the review of this. And that's a summary of why I chose mini sumo. So let's go through now and walk through the actual, as I talked about, the design steps. The first step is to break down your inputs, your requirements, and then transfer all of that into a finite state machine diagram. So now we're going to walk through what my actual diagram is here for this system, for a simulator for a mini sumo robot. Okay, now let's see here, up. I hope that is legible and seeable. Okay, so I'm just going to mention this. I mentioned that I'm going to be showing you a video in just a short while that will go through all of this detail in more detail, but I just want to highlight this diagram. It has, this machine encompasses 5 different states: countdown, hunt, survive, target, and attack. Now, there are 4 inputs for this machine. In other words, 4 sensors that will eventually be put on the physical robot that need to be captured and simulated for this robot. And those are 2, a left and a right, edge detectors. In other words, to detect if the robot is just about ready to move out of the ring. So that's 2 of the inputs. The other 2 are the front-facing object detector. In other words, looking for the opponent. In other words, a left and a right individually, object detect, front-facing object detect. So those are the 4 inputs that helped me put this finite state machine diagram together. And as I say, I'm going to defer exactly all the design elements, the way that the transitions happen. I'm going to defer that for all the meat that's in the video. Okay, I don't want to belabor this any further. Now, one thing that I want to comment about is melee versus more machine. So in this particular case, this is a melee machine. And that's because the state and transition changes that are designed into all this that eventually turn into different outputs. In other words, a new state, that those changes don't happen. Let's see, I'm sorry, that they're not only dependent on the current state. In other words, if we're in hunt or whatever, that they don't only depend on the current state, but also on the inputs, the mix of inputs. So that's why it's a melee machine. Okay. All right, so enough on that. Now we're going to do a brief walkthrough. Again, this is going to be part of the repository collection of materials that you all will have access to if you wish to use it, and is the actual Arduino code. Is this finite state machine was implemented in a single code file for Arduino. I ended up using the Arduino IDE for the development environment for this, and therefore the typical setup function and loop function is used within this. And then the overall architecture for this machine mimics that other file that we looked at earlier, as far as using the way that the states and the enums and all that kind of stuff are actually implemented. So I'm not going to belabor this too much. I'm going to put a lot of the responsibility on you, the audience member, to go through and understand this a little bit further. But I just wanted to go through a little bit, point out some interesting points and specifics that you need to reference in, because a lot of this is just literally cut and paste, so to speak, for the overall architecture design that we talked about before. Okay, so one thing that's real important here. So this top, of course, is the prototypes and the declarations and the actual interfacing, hardware interfacing elements, declarations, and all that. Okay, so that's what's up here at the top. Okay, and then of course, then the type defs for the current state capture and or the next state capture and all that. Okay, so again, real similar to what we looked at before. And then setup is getting everything initialized, including calling the initialize state machine function. Okay, the first thing I want to comment about is to do with what happens within the while loop, or in the Arduino IDE environment, the void loop function, which basically replaces the C standard of calling main. Okay, now what's going to be kind of unique here is that I've got a check here. This here is an actual shortcut of the survive functionality or survive state that the simulator needs to use. And the reason why this is called out here, this looping function is handling the do forever, the continual while loop that the machine needs to stay in. And so what we're doing here is we're looking at the left and the right bottom of the robot facing Dehoto check sensors. So that's what this code is doing. That's what this is here that I've got highlighted. Okay, now, so the reason why this is called out here, in addition to a separate survive state, is that this is mimicking, this is like if you look at it like a non-maskable interrupt or the highest priority task in a system. Okay, the survive functionality of the robot is that. In other words, to survive, to stay in the contest, this has to be the highest level immediate action take functionality or state. And so we're always looking to survive. And so this is a design technique that is used here to handle the non-maskable interrupt type of functionality. And then if we're not in, if that is not detected, or if it is detected, then we automatically go into the survive state. And therefore the state transition for the function pointer will automatically go into survive and handle that, and then move on in the rest of the finite state machine. So that's the reason why this design technique was employed here, because this functionality needs to behave like a non-maskable interrupt. So that's why I've got that specifically called out here. Okay. Okay. And so beyond that, because one one of our inputs is not a clock timer, that's why this while loop is so simplistic. And that's one of the great things about this design technique, okay, is we're just literally calling into the state table. What's the next state that we need to get into? Or what is the state that we're going to transition into next? So that's why this line is important, okay? Now, the other thing, again, I don't want to belabor this, okay? But there are lots of delay. Now, this here is a Arduino function call. There are lots of these delay loops, or sorry, function calls in here. And I put these in multiple strategic places within the code base because we need to slow things down so that the simulator, so the actual UI, what the user is actually seeing as an output of the simulator, so that it's actually noticeable. Otherwise, everything just goes by so fast that the user doesn't even know that it's happening. And so we've got lots of delay loops in here in strategic places, okay? And also to help enumerate the need for continual check for survival. A lot in the majority, in fact, in all of these states that I have defined for this machine, we are going in and checking directly if we need to be in the survive state next and be able to handle that directly. So in multiple places, we are checking for survive. Okay, so basically all of the state functions will have this type of functionality embedded in it. It's at the end traditionally of the states, handling of the functionality within each state, because at the top of the while loop, we had already just made it a state, or let's see, a state check for survive. So that's why it's at the end again for each state. Okay, so those are important details. The other thing that I want to talk about, a big part of the UI, is use of an LCD screen for textual output. And what I found out that I needed to do so that the screen was readable at any one time or another is I had to add in a check, specifically with this type of functionality here, a check of, I had to add a flag in here for specifically, well, with one of the functions that's in this design, for checking to see, well, now has this particular text already been shown on the LCD? And so that's what this particular variable has to do with. Again, that's just kind of a side point. I just wanted to mention it. Okay, so I know that that was a quick overview of the code, but again, I don't want to belabor that too much. Okay, now the next thing that we're going to do is we're going to do an actual, I think what we want to do before showing this video is we want to take a quick 5-minute break. So Steve, if you could set up a timer for us for 5 minutes, and I'll go ahead and stop. I'll go ahead and stop sharing right now, and then we can go ahead and we can do our video for actually demonstrating and walking through the design process closer of the finite state machine simulator. Okay, would that be all right, Steve, if we do a 5-minute break?
That will be just lovely. I will do that right now. All right, so it's currently 2:40. I guess we'll call it 2:44. So about 2:49. Let's all come back. Oh. Sorry about the time zone thing. Sorry. 11:49. I think that must have been Eastern time or something there that it jumped in with, or was it Central? 11, 12, 1. Yeah, I guess that would have been, no, that would have been Eastern. Yeah. Hmm. Hmm. Okay, I think we're just about, that's just about 5 minutes there.
Okay. Okay, great. So I'll go back to screen share here.
Okay.
All right. Can everyone see my screen?
We're seeing you.
Okay, do you see? Okay, so it should be ready to play the video is what I'm asking. If the video.
Yep.
Okay.
That's what it looks like. Yeah.
Okay, so let's go ahead and do this is going to be a full walkthrough of the simulator.
Okay.
Hey, Donna here again. So we are going to review in more detail the finite state machine for the Mini Sumo robot simulator. And so we're going to look closer at the finite state machine diagram itself. And we are also going to do a review of the actual hardware, the interfacing that I did to build this simulator to the Arduino Uno microcontroller. And so we're going to look at the interfacing parts that I used to design this. And then we're going to look at the schematic itself that reflects that design. And then lastly, we're going to do an actual demo on my workbench of this simulator in action so that you can actually see all the detail that reflects my discussion. So let's get to it. First of all, let's look a little bit closer at the finite state machine diagram. So as we've previously talked about, this machine is comprised of 5 different states. The countdown state is the initial machine entry point. That's why it's marked as enter here on the diagram. And that reflects the mandatory per the Mini Sumo contest rules that the robot remains stationary for 5 seconds before beginning any movement on the Dehodo ring. And so there's a 5-second timeout delay that actually transitions that countdown stationary state of the robot into the hunt state. Okay, so it's within hunt that that's kind of the main working, so to speak, state of the entire design. And so we spend a lot of our time in the hunt state. The idea of the hunt state is that the robot is not at the Dehodo edge, and also it has not yet sensed a presence of an opponent. And so the robot needs to be continuously moving around looking for the opponent, and then transition and do transitions based on that type of activity. Also, to refresh your memories, there are 4 different independent sensors that comprise this simulator and eventually the physical robot. We have the left and right floor facing edge detector sensors that look for the ring edge. And then we also have the left and right forward facing from the front of the robot object or opponent detector sensors. Okay, so there are 4 different push buttons in the simulator that simulate that sensor has seen something that needs to have the machine react to it. And so that is the sensor combination that this machine needs to handle. Okay, and so another important state is target, and that state reflects the fact that an opponent has been sensed ahead, and that the robot needs to face the opponent directly to initiate any state change. And then lastly, there is the attack state, where the opponent has been found, and our robot is directly facing and aiming at the opponent, and then initiating the drive forward, full forward drive power to push the opponent out of the Dehodo. And so that's what the attack state reflects. Okay, and so so as I said, we're in the hunt state, and the hunt state initiates a change to the target state when either the left or the right, or both the left and the right front object detector sees the opponent. Okay, and then it transitions out of target if there's no object detected. In other words, if we initiated in real life, if we got into the target state and then the opponent was a fast mover and got out of our line of sight for the object detectors, and then the opponent is there no more, then we transition back to hunt to continue looking for that opponent again. So that's the reason for that, those two transitions. And then next in line, we've got the target state. And so target needs to switch back to survive state if either or both of the edge detectors target or sense the ring edge. So that's what happens there. And then also out of target if the object detectors, both left and right together, have seen the object, then we move into the attack state to actually initiate the extraction of the opponent out of the ring. So that's the reason why we go in from target over to attack. And then once we are in the attack mode, then we need to check to make sure that both the left and the right together front object detectors are still seeing the opponent. And if they are, then we do a full forward move, and then we are in the full attack mode. We are pushing the opponent out, and then we trigger back from attack to survive whenever we have initiated the full extraction of the opponent. They are out of the ring and our robot is at the edge. So then we need to switch back into survive. The other way that the attack state can move into something else is if we got in there into attack and both front object detectors are not still active. Then we go back into hunt state. So that's kind of the overall logic here. Also, I neglected to say that when we are up in the hunt state, if we're hunting and we encounter either the left or the right edge detectors for the Tohoto edge, if either of those are sensed, then we trigger and we go into the survive state out of hunt. And then also with the survive state, the way that we get out of that is if there's in survive, what happens is that the robot does an arc or a rotation, depending on which of the two sensors was activated, to get back in, reposition itself back into the center of the ring. And so the way that survive gets itself out of that state is when the rotation of the robot is complete. So that's why that transition is shown on the diagram. Okay, so enough about the transitions and details on the diagram. Now let's look at the actual hardware parts that comprise my simulator. Okay, so I'm using the Arduino Uno R3, Rev 3 of the board. I'm using the barrel connector that's on that microcontroller. I'm using 5 AA batteries. So I've got a 5 AA battery holder with their respective cells that's powering the board and the entire system. I'm using so the big part of this, of course, is the UI, and one important part of the UI is an LCD, and so I'm using a standard size 2x16 serial LCD unit, but this is a special parallax module where only one I/O line is required to interface to the microcontroller. Okay, and then I've got a total of 5 LEDs that reflect different state changes, different functionalities that are happening in the simulator. Again, an important part of the UI are the LEDs. And so to interface those LEDs to the controller, I'm using 5 330 ohm resistors. And then also another big part of the UI are the switches. And I'm using 5 push button tactical switches, and I need 5 2.2 k ohm resistors that are interfacing those switches to the controller. Now again, those switches are what actually triggers the various scenarios, state changes in the simulator, because those 5 switches will be starting the robot or the simulator, and then we have for the individual switches for each of the 4 sensors that I talked about earlier. Okay, and then we've got the 5 push button tactical switches that I mentioned, and then the LEDs. I've got various colors that I'll be showing you that reflect the various states and happenings of the simulator. I'm also using a solderless standard breadboard and 22 gauge hookup wire to hook all this together, and any needed cables like a 3 connector cable that interfaces the LCD over to the pins on the controller. Okay, so that's the hardware list. Okay, and then also lastly for diagrams, here is I created the schematic using the fritzing environment. And so we've got the 5 LEDs, the 5 push buttons, and we got the Uno board, Arduino Uno, and then that small looking part that is near the top portion of the diagram that's more black than anything else, with the 3 connectors that are shown there. That's a representation of the LCD. Okay, and so as I said, this is a special type of part for an LCD where only one I/O port is required to interface, and then the plus 5 volts and the ground connectors. So that's the reason why why we're not seeing an actual LCD display on this diagram. Okay, so that is the physical hardware diagram. All right, so now we're going to go ahead and actually do a run through. What you're seeing right now on the screen is my actual physical implementation of all this that we've been talking about, both before this video and during this video. And so what you're looking at right now is the actual UI that's connected onto the breadboard itself. And then I want to move the camera slightly so that you can see the remainder of the simulator. In other words, the Arduino Uno itself with all of its connector wires, along with that battery pack that I was talking about. Okay, so now we can actually physically show the simulator itself. All right, so I've got okay, so important notes here. Okay, so the LCD is used exclusively for textual type comments and state changes and information that's going on within the simulator. And it's I'm using that LCD in that context. The LEDs, so there's a total of, as I said before, 5 LEDs. So this one over here is showcasing the start action. In other words, that to initiate the countdown out of the countdown state, this LED shows that activity. Okay, and then this LED here, the yellow LED, shows activity of the survive state. The green LED right next door to it shows activity for the hunt state. The next one over, that's a standard red LED, is for target state. And then the very last in the row LED, the darker red LED, shows activity for the attack state. Now there's some extra information besides just lighting of these LEDs and text reflected on the LCD that I want to comment on. When we are in the attack state and the opponent has been knocked out of the ring, okay, right before we switch out of attack and get into survive, because the edge detectors have been triggered, it goes into survive. Right before that, I show on the rightmost start LED that the opponent has been successfully knocked out of the ring, and that LED comes on during the attack state to showcase that. Okay, so that's a dual purpose for this rightmost LED. It's going to show a pulsing 5-second countdown during the initial part of the simulation, and then the other part that can be triggered is during the attack state to show that the opponent has been knocked out. Okay, so that's one exception to the normal flow of the LEDs. The other one has to do with the hunt state. That LED, besides just having a solid on lighting of it during when it's in the hunt state, it will also, I have a flashing LED for hunt showing when there is no opponent that has been sensed yet. So that LED will flash within the hunt state itself when no front-facing opponent has been seen ahead. Okay, so that's kind of the overall feel for the UI for this environment, for the simulator. Okay, so let's go ahead. So right now, so as soon as I'll go ahead and refresh, do a reset on the Arduino again, and so the initial state display on the LCD is showing that the simulator is ready. Okay, so right now we are waiting to even enter the finite state machine. We are up at that upper left hand corner of the machine for enter here. We haven't entered yet. Okay, so now we're going to go ahead and we're going to initiate, we're going to start the robot. We're going to start the simulator. Okay, and oh yeah, and I forgot also to mention about the push buttons. Okay, so we've got 5 different push buttons where it's a press and release. Okay, and so we've got the start button to initiate the start action of the robot, and then the next button over is it will be pushed when the left edge is detected on the robot. So that's the left edge detect. The next one is for the right edge detect. Next one is for the left object detect, in other words, those front facing sensors. Left object detect, and then lastly right object detect. Okay, so that should comprise the UI. All right, so now let's go ahead and initiate the simulation. So we go ahead and press and release that. We've got the countdown timer going on. Okay, so now we have initiated out of the countdown state, and now we are in the hunt state. Okay, and so the reason why we've got a green flashing LED is that we are actively hunting. There's no opponent seen yet. Okay, and so now what we're going to do is, just for grins, we are going to transition from hunt over to survive. Okay, and the way that that happens is when an edge is detected, say the left or the right or both. Okay, so we're going to go ahead and we're going to indicate that the left edge has been seen. So then we are in survive state. That's why the yellow LED is showing. Okay, so now we've rotated out of that, and now we're back in hunt again. Okay, as seen in the left hand side of that finite state machine diagram. Okay, and then we've got a right edge detect, for instance, and so now we're going to go into survive state again because we are counterclockwise rotate out back into the center of the ring. All right, and now there's no more edge, so now we're back into hunt again. Okay, and then if both left and right together are activated, again we're in survive, and we have to do a complete 180 to get it back into the center of the ring. Okay, so that's the transitions that happen between hunt to survive and then survive back into hunt. Okay, so that was a demo of that activity. Okay, and so now let's talk about from hunt over to target. The idea about whenever the front-facing opponent is seen or not. Okay, so if we are in hunt and say that the left object detector is initiated. Okay, and so we've done that, and now it's transitioned over to target. Okay, but then if there's no object that is seen, then it goes back into hunt. So let's do that again. So if we have a left object that's been sensed, it goes over to target, and there's nothing that happens because there's both left and right together object detectors are not active. So that's why it goes temporarily over to target, and then it goes back to hunt again. Okay, that's ditto for right object detect in solo. Okay, so it goes back into hunt. But if both left and right together are initiated, again we go back into target, but if the object disappears, then we go back into hunt. So that's the flow between hunt to target. Okay, now let's talk about the target state. Okay, so let's talk about target to survive initially. Okay, so the way that transition happens is if we see an edge, one or both of the edge detectors are triggered. Okay, so let's handle that. Okay, so we've got left. Okay, so let's just say that both left and right object detectors are present. Okay, and now we've got, okay, so that transition was the idea of that a left edge was seen within the target state. We switched temporarily over to survive, which was that yellow LED on briefly. Then that rotation was completed, and now we're back to hunt again. Okay, so let's do that one more time. This time let's just do the left object was detected. We'll go into target, we'll do one of the edge detectors, which will go to survive, and then back to hunt again. Okay, so that's the type of activity that happens there between target to survive. And the only option for getting out of the survive state is to handle that rotation that needs to happen to get the robot off of the edge and therefore back into the hunt state. So that's what we are reflecting now within the simulator. All right, so now let's talk about target and going from target into attack. All right, and so the way that the attack works is if both object detectors see the opponent, then we go into attack, or at least we initiate going into the attack state. And if the object is still there in both left and right objects, then we actually go full forward. We are aiming at the opponent, and we are initiating to knock the opponent out of the ring. Okay, where then we go from attack into survive. Okay, now if counter to that, if we if both object detectors are triggered at the same time, that initiates target into attack, and yet the opponent disappears with either one or both of the object detectors, then we go back from attack back into hunt, because the object is no longer there to directly attack, to move it, to force it out of the ring. So that's the transitions that happen between target and attack, and then either attack into survive to knock the opponent out, or attack back to hunt. Okay, so we're gonna take care of demonstrating that activity. Okay, so first off, let's assume that the object is still in view when we are in attack. All right, and so we're doing that, and now we're doing that again. Whoop. Okay, so all right, so that was a demonstration of that second part where we went from attack back to hunt, because the object was no longer there. It was no longer present when we got into attack. Okay, but let's go ahead now and let's do the other. Okay, so now we're in attack, and now we are actually, well, there may be a fight right now going on in the ring between my opponent and me, and yet I am initiating, extracting that robot out of my opponent out of the ring. So that's what's going on right now. Okay, and so that's why we show on the LCD that the opponent has been aimed up. We are full speed forward. Okay, and so now let's say, so now right now we are in attack, and we are in the attack state, and the way that we get out of attack is that either the left or the right edge has been detected, or both left and right together. Okay, so that's the way that we get out of attack. All right, so now we are going to say that both the left and the right edge have been detected together. Okay, so we're gonna, all right, so see that rightmost LED was on briefly. That meant that the opponent was actually knocked out of the ring successfully, and we went into survive state. That yellow LED came on briefly to show that we had to go into survive to do a rotation to get out of, or to get back into the center of the ring. So we went into survive briefly, we completed the rotation, and now we are back into hunt. Okay, so that's literally an overview of the finite state machine. Okay. Okay, so I will conclude with this recording, and we'll go back to the presentation. Okay, guys. Hopefully that was informative for all. I know it was kind of knee-deep in details, but that's what we needed to really understand this finite state machine. Oh, let's see. Can you guys? No, you can't hear me. Can you,
Yeah,
can you hear me?
We can actually, yeah.
Oh, you can hear me.
Mm-hmm.
Okay, great. All right. So now let's round out this presentation by talking about what my next steps are. So ultimately, I want to take the root parts of this simulator and physically implement it on a mini sumo robot platform with the accompanying set of 4 sensors and possibly a small LCD for additional UI on the physical machine itself. And so that's my overall next step with this design. And one of the things I want to comment on, I mentioned this briefly before, is the idea about how beneficial for experimentation anyway in robotic in robotics, but especially for something like a finite state machine, where the transitions and your definitions of the state really should be verified in an easy software methodology, where a simulator like what we've just reviewed can really be beneficial. What I'm suggesting here is the use of a simulator type of design initially before you actually port your finite state machine to an actual physical robot. I think that that's a great way of designing, implementing, and verifying, aside from having to worry about hardware incompatibilities or specific errors that you might be having with hardware. It's great to verify singularity of your finite state machine diagram itself. Make sure that it's valid and foolproof, bug-free before actually moving it into a physical robot environment. So that's why I recommend that you initially start with a simulator. Okay. So for my specific simulator itself, I wanted to point out the idea about the LCD. I'm sure that you saw in the video that the LCD was not overly clear as far as the textual output was concerned. I had problems at times within the design for the UI of being able to more fully use the LCD text output. I had problems with that because of the idea about the forever looping action that happens automatically within a finite state machine. And where, in other words, where the text is scrolling so fast that you can't necessarily see it. And if you guys take offline, if you guys go ahead and take my code base, implement your own simulator, either a direct implementation or coming up with your own, and utilizing an LCD, you will actually see physically what it is that I'm talking about, where the text isn't necessarily all that usable. So that's why I came up with other UI elements to compensate for that. So that was one thing that I was really quite surprised about. So just wanted to mention that. And also, as far as moving this simulator to the physical robot, one thing that's not directly reflected in the simulator is the idea about what happens specifically in the target state and moving from for the decision making between target to attack is I'm not actually checking anything to do about distances as far as those two front object detectors. I'm not actually looking at anything to do about distancing. Well, now, am I really lined up besides actually seeing in the line of sight the opponent? I'm not actually looking at anything to do about distance. So in other words, the idea about making sure that that opponent doesn't escape out of my view before we start butting heads literally in the ring for me to be able to push him out of the ring. So that's one thing that I need to add for the physical implementation, is factoring in distance. Okay. And I also mentioned this during my brief walkthrough of the code, those prudent uses of the Arduino delay call. That, of course, will have to be, the use of those will have to be reevaluated for the physical robot. Likely, there won't be really any delays that will need to be added for the final finite state machine implementation. I may not use an actual LCD, depending on what happens with the actual robot design itself. And of course, then the actual motor movement commands will all have to be rewritten to actually interface to the actuators. In other words, the two servos on the platform itself for the motor commands themselves. And of course, the actual hardware and software drivers will need to be rewritten for the actual physical platform. But most of and that's what the whole idea about developing a finite state machine in the simulator world first, and then moving it over to the physical robot implementation, is I suspect that the majority of that code base that we have walked through and that I'm going to be providing to you is usable in the real robot implementation. Okay. Let's see here. Okay, so some suggestions about taking what we've reviewed, learned about today for you individually to take this to the next level. So I recommend that you create your own simulator for finite state machines, either basing it directly on what we've talked about today, coming up with your own simulator designs, and really test and experiment with this basic implementation of a finite state machine. It's very customizable. It's a great learning environment. It's a great way to improve your robotic skills to become proficient at finite state machines. And I hope that I have shown and proved that to you today. You can move then your simulator to a physical robot design, as what I'm going to do in the mini sumo contest. And you can build bigger systems to include multiple finite state machines. I mean, the mini sumo model, of course, is not a good representation for that, but there are lots of other robotics or embedded systems where multiple individual finite state machines make a whole lot of sense to develop separately and then combine them for the totality of the system. Okay. You can utilize other architectures, real-time operating systems. Now, specifically on the Arduino side of the microcontroller camp, there are multiple, not necessarily full RTOSs, but real-time kernels that are available that are directly usable on Arduinos. So that's one way of utilizing a multitasking, multiple task environment along with finite state machines. There's also the subsumption or behavior-based design method that goes right in tandem with developing finite state machine modeling for your overall system. So those are some other ideas for how to take your learnings to the next level. Okay. And so now I kind of want to open the floor for additional questions. I will be, once we get through this, I'll go ahead and provide in the chat that shareable link for your repository of files and information. Okay, so open the floor to you.
Okay, I'm going to jump in with just a couple of comments and questions here. So it sounds like using LEDs as your state indicator, having LEDs on your physical robot will probably be a good way to be able to tell that it's interpreting things correctly and it's doing what you want it to do.
Correct.
A general question: what drawing tool did you use to create your FSD diagram?
Sure. Yeah. So the for the diagram itself.
Yeah, I know you used Fritzer for the.
I used fritzing
for the Arduino.
Right.
Yeah, the other one, the FSD diagram.
Right. So all that I used Visio, Microsoft Visio for just kind of the basic flow chart or drawing tools. But really that's one thing that we didn't have time to go into today. There's a whole slew of finite state machine support drawing and design tools that are out there. I ran into several when I was researching this topic for today's talk. There are some specifics that directly model. In fact, they'll even generate C or C++ code for you once that you've designed your finite state machine diagram. So there's lots of online tools that are out there for both code generation and also for the diagramming. but just go ahead and
Okay.
keep it simple to start with for your diagram, because it's always better to get your feet wet with actually writing the code yourself versus automatic code generation. I think that's always a smarter way of doing your designs. And then once you get more sophisticated, you can use automated AI tools to help supplement your design.
Okay. I was thinking about when you were talking about, you just had basically the four sensors, but I was thinking that, like, if your opponent is pushing you back toward the line, you might want to do something different if your back end of your robot is detecting that edge. And so sounds like it could be useful to have one or two additional sensors looking down at the floor on the back end of your robot as well.
That's right. Yeah. This was just a basic kind of demonstration of minimum level functionality that that a mini sumo could employ. But yeah, in fact, to that end, as far as whenever you're in the attack state and that duel is going on within the ring, I think that besides the rear edge detectors that you mentioned, Steve, another great sensor to be adding in is the idea about tilt sensing or angle sensing. So in other words, if if you detect that your robot, you yourself, are being potentially pushed out and that you're not applying necessarily enough motor power, that you can maybe augment your software algorithms to apply more power or to back up, get yourself repositioned and then re-attack again, kind of thing. So there's lots of that attack state, I think, is very tenuous as far as additional changes that can happen, as far as adding in additional sensors or even different control logic, depending on what the robot is actually happening to that robot during attack.
Right. Okay. Yeah. I hadn't thought of the tilt sensors. That's a great idea.
Ready for other questions?
Of course. Yeah. Go right ahead.
So, first off, great talk. I love the practical example. I've written a lot of code over the years that's used state machines, but to be completely honest with you, the one thing I have never really understood is what the heck actually is the difference between a Mealy and a Moore state machine, because the thing is, they both use inputs, they both accept inputs from the outside world. It seems from what I've read in the past and what I'm reviewing today, the big difference seems to be related to how those things are clocked, how the state changes are clocked, and whether the logic for transitioning based on input is handled outside what they call the state machine or inside what they call the state machine. But those all seem like such subtle distinctions that I'm wondering if they're even worth thinking about. So I guess my question is, do you see a significant difference? And in your mind, what is the significant difference? And is there any point in worrying about the difference?
Well, yeah. First of all, as I mentioned about during the formals of my talk, is that really the distinction between Mealy and Moore are really not important. It's more of an academic exercise to understand the differences between the two. When it comes right down to rubber meeting the road, so to speak, what's more important is to understand your system, what it actually needs to do, and making sure that your design is simplistic enough that as additional states and features of a design need to be added to your modeling, that your current design will allow for those additions. I think that that's an important part of this modeling scheme. And the idea about knowing when you are dealing with a mealy versus more machine, I think is just purely academic. It isn't really something that's too important. Now, in the repository of information that I have shared with you on Google Drive, there's a PDF file that's in there that is super duper important I think for thorough review for everyone on this call today. And it's a 2-page document. And on page 1, they talk about a little bit more about what a mealy machine versus a Moore machine are. And then on the second page is that basic C language architecture design that we employed for this simulator today. Okay, and then they also give you details in there about the accompanying finite state machine diagram that goes with the C code example. Okay, and then they talk a little bit more about the inputs and the state changes, and then a little bit more about the overall 3 states that were chosen for their machine implementation. But to your question, the idea about the intricacies, the subtle differences between a mealy and a Moore machine are really not unless you're looking at it from the academic sense, they're really not. I don't think they're really important. As I said before, what's important is that your model correctly reflects the needs of your system, that it's simplistic and expandable with the modeling that you're doing. And, and those are the types of things that you need to look at versus,
well, I want to say thank you. I just want to say thank you for saying that, because I've heard a lot of people get really lost in the weeds on that.
Oh yeah, and that's one of the reasons why I wanted to focus on a topic such as this for this presentation today, because there's so much noise out there, so to speak, about multiple types of finite state machines, different methodologies. Say for instance, especially in the design patterns and UML world, there's a whole slew of documentations and design patterns that are, well, not design patterns, but design pattern, specifically the state pattern as defined within UML. That is a basic computer model for the way that finite state machines can be handled. There's a whole, there's a whole, what I try to focus on today and what I'm trying to impose to all of you today, especially like to do with distinctions of mealy versus Moore, that type of thing. What's more important is to cut down to the basic core elements of the design from there, just concentrate on coming up with a great design that is modular, expandable, solid in design, test it out with simulation first, and then move and expand and grow your skills in finite state machine design into other areas. Once that you've got the basic core, something that's really solid that you can really understand. Once you get to that state, then you can move on to more academic lessons and learnings, and getting more into UML and design patterns, specifically the state diagram. I'm sorry, the state design pattern. All that kind of stuff. So that's what I'm recommending, and the comments on that.
So yeah, again, thanks for that. The other thing I wanted to, it's not really a question, but you mentioned assumption architecture kind of, as being one application of state machines at the end of the thing. And I just want to throw out that I just absolutely love assumption architecture. And I see a lot of like beginning robot makers who really miss the ball by not making use of those in cases where it would be really easy. So just in your little robot example, the point there is that you have these different behaviors and or these different states, and you're moving from one state to the next, not just in a pre-programmed way, but as a result of some external input. So, one of the things that I see all the time is like gate generation as a fixed animation, as opposed to gate generation that is run by sensors, run by feedback from the actual, legs that are moving. And it's a really small change. It doesn't take a lot of extra effort to, just embed a switch or maybe, use a servo that has some kind of a readback system. Adafruit makes those, and I really recommend them. So anyway, I just kind of wanted to push people to look at subsumption.
Yeah, I agree. I do agree with you, James, on subsumption.
And maybe that's a topic for a future talk.
Right. Yeah, exactly. Yep. I agree with you. Okay. What other comments or questions or whatever do people have?
Well, if nobody else has a comment, I'll make one more small comment. It's getting him to shut up. That's the trick. Anyway.
Well, that's easy. I just mute you.
Yeah, you got me there. That's what it would take. Anyway, the point is, what I was going to say was, one of the things I noticed about state machines, and this is kind of feeding off of what you were saying about, like which exact type it is doesn't really matter. Just, understand the system and get it done. A lot of the state machines that I end up making end up not having a specific variable to track the state. Instead, the state is determined by the settings of multiple variables. So for example, if I'm decoding a protocol, it's like, have I received the header or have I received the start signal? And then there's another variable maybe that, like, if that's true, then, have I received the address? If I've received the address, have I received the data? Have I received the CRC, right? So I might have, a quote state machine it's a really, weird way of doing it that, says something like, is the header not 0? Is the address not 0? Is the data not 0? Or maybe it's, not -1 if you want to have a 0-based address. Is the CRC not 0? Oh, well, then I've received the whole command and now I can go on. So in other words, I'm just trying to point out that it doesn't necessarily have to be like one variable that's an enum that controls it. You can have states that are, sort of built up by looking at the status of different, different variables.
Right.
Anybody know of a good Macintosh diagramming software for making the finite state machines?
I think, Terry, that a comment was just put in chat specifically to that point.
Oh, I see. Thank you. I didn't catch it.
Yeah. I mean, just as you were phrasing your question, it came through.
Awesome. Thank you.
Well, I hope that all of this has been beneficial to all of you. It gives you potentially a new design arsenal tool for your robot toolbox. I know it has sure been insightful for me to work on this project and to put all this together for you. It's been very enjoyable, very rewarding. And so.
Thank you, Donna. It was a great presentation.
Thank you.
I totally agree. Yes. Thank you so much. And yeah, you put a lot of work and time and effort into it.
Yeah,
really
I did.
Yeah. It's you learn a lot when you do that, don't you?
Yes, you do. Yes, you do. I encourage all of you to consider doing such activities and presenting more at the SRS. It's a great, great venue.
everybody here in the group, everybody online is you know, we would love to have presentations, hear things from you guys. I know some of you have taken me up on that, and yeah, so just reach out to me if that's something that you would like to do, because we would love to give you that opportunity to have your you know, 15 minutes of glory. So
Even if it goes on for an hour and a half or more.
yeah, you may have more than 15 minutes, you know, it could actually be an hour and a half. Yeah. And okay, I'm attempting to share my last slide here, and so you know, we can continue to chatter while Zoom gets around to putting it out there. But maybe I'll just go ahead and read off of it here. Thank you so much, everybody, for joining us. This has been fun as always. Same link next month, and I believe I have I think I have the calendar fully updated, so all of the upcoming presentations will appear when you go on the website. I think you hit calendar in the drop down, and it'll show you what's coming down the pike. Next month's meeting will show up here in the next couple of days. The meeting recording will be available on YouTube, on our YouTube channel, probably in a few days when I get around to it. Well, I'll keep the website up to date with any changes, particularly related to in-person meetings and such. I have a note to help me find presenters, but you know, Robert, keep it up. I appreciate the constant stuff coming in. If you have any feedback for me, just send it to Seattle Robotics Society at Gmail. And thank you for sharing on the chat. And if there's anything else that you want to throw in there, please do. And thank you for attending today and supporting us. And hope you have a great rest of your weekend. And I will go ahead and stop recording, but we can continue to chat as anyone sees fit. So thank you again, Donna. Thank you, everybody.
Well, thank you. It's been fun.
Thank you.
Yeah. So that was great fun. I'm actually kind of interested in playing around with that in the make block graphical environment, the Scratch environment of those robots, because you can do you actually when you have the robot connected via USB cable to your computer or Chromebook, you are actually running a simulation of the Arduino processor on the robot, but you're not actually running in that processor. You're running it in the cloud, and so you can see everything that's happening. You can see variable values. But you can also see the physical effects on the robot. So you can control motors. You can control LEDs, read sensors, and all of that kind of stuff. And so I was like, okay, I've not implemented that kind of a software architecture on there, and it's like, oh, that might be the way to solve some problems that I've run into in the way that I've been trying to do it. So I'm kind of anxious to give that one a shot. So I'm looking forward to that.
Cool.
Richard, I trust that my son got you taken care of with the SRS email.
He did.
Business.
Yes.
Okay. Awesome.
We're in good communication. I did finish my half, and I just haven't gone back to Alex. But I'll get him. We're not in a hurry.
Yeah. Good. No. It's yeah. Good. He's pretty good. I mean, he's pretty good about following through with stuff. You know, I'm one thing I'm a little bit concerned that our discussion prior to starting out, we were talking about Chat GPT, and he's just finished a software training program so that he could be a programmer somewhere, and it's kind of like, well, now AI might replace him.
Like, you know, just like anything else that's automated, you know, it's better to be on the leading edge of where you can be the person controlling the automation. It's not like you don't need those skills you know, someone still needs to train it. Someone needs to know what to put into it. And those skills are generally the same ones you'd need to learn if you could do it yourself. And it's really true for any of those software tools that, you know, sure, I could lay out a circuit board using Mylar tape and a photographic process like we used to do in the 70s. But, you know, just because I have fancy layout software doesn't mean that it's doing it for me. I mean, certainly I make fewer mistakes. I can do it faster. I can do it better. But, you know, it's not coming out going, well, I'm going to design an amplifier today and lay it out for you. And, you know, ChatGPT is kind of the same way. It's like, yeah, it's just sitting there waiting for input. But, you know, it really depends on what input you give it to get really good outputs. I mean, from like Lloyd's questions that he is posing for his mock interview, you know, they're good questions to ask any interview person, but you know, it requires enough good input to get a good output, and knowing how to ask those questions and how to parse that output, you know, even when it's a real person, you know, those are the skills that really keep you working.
Well, it sounds like having GPT as a discussion, I think, is liable to be a I want to see I want to see some, you know, I mean, let's show me some interaction too, you know, do some live interaction with it, and let's, you know, see what it can do. And yeah,
I'm sure that someone's got a Discord bot that allows you to tie into ChatGPT. So we'll get ChatGPT. Maybe we can get that when we get the Discord channel up, and we can have it as one of the participants.
Oh, now that sounds like fun.
I did toss up a video up in the chat for you.
Oh, okay. Okay.
It's just one very, very silly one.
So now, is that one that so it says just built entire app in minutes?
No,
so that's, did you just do that, or is that somebody else?
No, that's not. That's Robert.
Oh, Robert. Okay. Okay. Oh, yeah. Okay, I see that. Yeah. Yeah. There is it's like if you look in just look in the chat history, there is like just a ton of stuff in there.
We've been
check out.
We've been playing with stuff.
Yeah, it's really cool. I love this aspect of Zoom meetings, because, you know, usually, you know, during a meeting, we try to kind of capture these things that we go, and invariably you miss stuff, and people think of things, but they don't mention it and stuff like that. And I love that, you know, you can just throw it out there when it comes across your brain, and it gets captured, and now it's available for anybody who wants to dig into it. So there is.
Have you done that in the Google Meet instead of Zoom? Because the Google Meet they have the chat, but they also have a virtual whiteboard.
Oh yeah.
So it allows you to just toss up like a scratch pad that you can draw on, and so all the participants can draw on it.
We have I think we have that here, and we have that in the Zoom meeting too. I think, you know, we've looked at the different tools for doing these meeting recordings, and the problem is that, you know, you kind of have to subscribe to something. You know, you have to pick one and subscribe to it in order to get the length of meetings that we have. You know, I mean, this is let's see, what was it, 10? So this is 2.5 hours. You know, so we need a long recording capability, and I think Meet kind of limits you as well. And just like, even like Zoom does, you know, Zoom limits you to 40 minutes if you don't have a paid account. And so since the SRS is actually funding the account that we use here, we have unlimited. You know, I think we can go 24 hours if we wanted to. Not that I would ever suggest.
I pay for Meet for myself because it's, you know, $7 or something, and now it gives you a terabyte of cloud storage. So it's like, well, I mean, it's worth it for a couple reasons.
Yeah, sure.
Many dollars than you. Happy.
You have more dollars than me?
Yeah.
Probably.
Oh.
Daddy.
Oh, there's all kinds of,
there.
Robert's been chucking all kinds of cool things up there. So yeah, it
Yep.
looks like
Yeah.
we definitely need to explore that some more. Yeah.
Yeah, I'll try to cull out some of my CES photos for you. I did CES, but I only did it for one day. I didn't even spend the night in Vegas. No, I flew down 6 o'clock in the morning and flew back at 8 o'clock at night,
Oh my.
and just did really all. I think I hit everything but one venue. But I got my 6 meetings in that paid for my $500 day.
Yeah. Wow.
For the
It sounds like that was a long day for you, though. Huh?
Oh yeah. I mean, there's my location history tracker on my phone has it marked as 12 miles of walking, and that's definitely not. It was definitely much more than that, because you look at the history, it's like, well, you miss. I see where I went into a room, you thought I was there, and walked out. It doesn't have the zigzags in each room. Very, very, very long day. But for as much as CES has had robots before, they've never, they've really just had toys. This is the first time that they've actually had, like, I would call them more, serious robots as devices that are useful for much more. I mean, not that robot vacuums aren't useful, but that's been kind of the only useful use case for having a robot around.
Yeah.
But they definitely had a lot more, particularly like for small business and small, medium-sized businesses, for goods, for transportation and mobility. Lots and lots and lots and lots of health robots, and then just some rather other random ones. They had the robotic food truck that was serving bubble tea. So you would just walk up to your touchscreen and order your bubble tea, and the robot would put it all together for you. And it's this big, like, performance-y type robot. Lots of extra arms than it probably needs, but
yeah,
it like makes bubble tea like a person would make bubble tea, as opposed to the way, if you're trying to automate making bubble tea, you would automate bubble tea. But they had the pancake printing robots out this year, and just a bunch of other small robots. So I'll put some of those together for you. But I did share one video for you that
sounds wonderful.
That I think would fit, that you would enjoy much more than.
Oh yeah.
But this, I'll just paste it again here so it doesn't get lost. But that's the one that you will enjoy.
Okay.
And it is just a toy. But I can find the link for that one if you want to, like, because they do have an online simulator for it if you want to play with it yourself without paying however much it was going to be. It's probably a $300-400 toy.
Cool. Anybody else? Not too many of us, only a couple of us left here yet.
Oh yeah.
Down to us diehards.
Yes. How's Amanda feeling? She doing okay?
We're doing okay. It's it's Chinese New Year, so we're prepping up dinner. I'm not prepping up dinner. She's prepping up dinner.
Nah. Keeping an eye on my, I've got a pellet stove back behind me there at the other side of the basement. Last night, the auger jammed, and I'm guessing that's probably because of maybe excess sawdust kind of getting into the mechanism or something like that. I could hear it trying to turn, but it wasn't, you know. And then it finally it starved itself. It wasn't feeding pellets anymore, and then it starved itself, and the fire went out. And I was in there earlier this morning, kind of cleaning out all the pellets, and then vacuuming out all the dust, and then kind of getting, you know, hitting the jamming a poker up where the pellets drop, and then up the auger as far as I could reach, is, you know, try to kind of get the pellets out of all the places that I could get to that it might have jammed, and it started running again. So I'm happy about that. But I don't know, maybe that's I don't know if that's the quality of the wood pellets you use or something. I don't know. Anybody get any experience with pellet stoves? And tell me if that's the.
Not I.
Yeah.
Yeah,
I had that on we had one in the house that we sold 3 years ago now. And, but it was a really old one. It was a really good one at the time, but it was probably 25 years old. And, you know, they kind of wear out after a while. And, so it had problems. It never actually worked all that great. And I had that same thing happen to that one a couple of times too, where the auger just wouldn't move anymore. And then it was the same thing. I had to clean all the pellets out of the hopper, and then start, you know, poking a sharp stick up all the orifices I could find on the thing to try to get the pellets out of the places where they could have been stuck. And it finally started at least moving again, but never really worked all that great. This one seems to work pretty well, but we've been using it a lot lately, and I've got 2 different kinds of pellets. So there was some pellets that were left here by the seller, which is more of a light colored, seemed like a more sawdusty kind of a pellet. And then I just bought some newer, darker ones. I think it's some kind of hardwood, oak or something like that. It seemed to be a little less sawdust on them, but they're mixed in the bin, so it's like, eh. So now I'm thinking about, how can I filter them? You know, I'd like a little sieve, a little sieve that I can like run them through, you know, when I take them out of the bin, to try to kind of get most of the sawdust off of them before I put them in the hopper. So
yeah, we have a wood stove, and has the heatilator fan on the back to blow cold air around the stove and out into the room. And that thing is the noisiest fan around. It's like you just can't use it, because it's like, yeah, sure, the room's warm a little faster, but you can't have a conversation.
I've got one of those thermal electric fans. I saw one at a friend's. We were visiting a friend, and they had one on there. I don't remember if it was a wood stove or a pellet stove, but they had one of these fans on there that just uses the little thermal electric generator. And it says, you know, if I ever have one of these things, I want one of those. So I went and got one, and they're very quiet. They're really cool, and seems like it works.
I got service tech training under my belt from way back when. And so in my experience with wood pellets is not as advanced as yours. I can find it that way. It works very well. And what you're probably talking about is, the first one is pine, where it's dusty. Probably out of pine, and I've also bought hardwood pellets too, and that's more for like barbecue. I don't have any real experience with the hoppers like you were telling me, but I imagine it's pretty much what you're doing to clean it out.
Yeah, I'm pretty sure the original pellets were some kind of a pine or fir. They're, you know, but it's a very light colored wood, whatever it is. So
it's light evergreen or the Douglas fir or whatever they try to use.
Yeah,
I would say this cat litter if there's enough of it, and it really reduces the smell down. I don't have to worry about smelling it, you know, when I take it out. And everything's biodegradable by that point. I like it much better than I've seen some automatic tumbler or something where you buy that crystal or something like that. But I've had people have told me the ones they have still smell it. If I have enough pumpkin pellets in the litter box, it works great. And if you need a kitten, pickle, I've got 3 kittens and 1 adult cat, and the pickles here is total handful. I need to invent some kind of a robot for each cat so they can wear it, but with a Velcro harness and stuff like that all day.
Yeah. Yeah, it's kind of that you're what you just said reminded me of there is for cat pellets there is a wood pellet based thing that you can use rather than the clay type for their boxes, and that got me to thinking, yeah, and I bet they've and sure enough, I went and looked that up. It's like, yeah, sure enough, they've got these nifty little scooping sieves and stuff for it's like, okay. Yeah.
Where I started with, but then I was like, well, wait, these are just wood pellets for a wood pellet stove. I just buy that cheaper, and I get more for 40 pounds for $5 or whatever a bag, instead of paying $20 for the smaller type in the feline pine bag, which does help for scooping. If you get the right scoop, you can. It may save you there, but I just use the wood pellets and dump it out. To me, it's very compostable organic solution that works much better than any clay or whatever else we put in cat litter. And I don't like the old clay stuff that's tight or whatever. That would have a dust in it. And urine would soak in. It's bad for long. Want to change it?
Yeah.
I'm still trying to copy everything that RJK put online.
That's Robert Kellogg.
Yeah.
He is a major internet researcher. That guy he can just amazing the stuff that he comes up with. So it's
just have a Google page.
Let's see. 3.
About finding the time, putting it in the right place.
Yeah, I'm looking on Amazon at all the choices of just sieves in general. There's lots of options. So I think I just need to go to the store and hunt through the household section of the store and just pick up something. Yeah, I'm sure I can find something that will just work well. There we go. All right. Well, got any? Looks like there's just a couple of us left here, and I'm 2 of them. my video on my other. You can see double of me now. my Zoom monitor there so I can see what you guys are seeing. Well, this was fun. I was looking forward to this, and it was awesome. So it's got me to kind of got the gears in my brain spinning. So I'm gonna have to play around with some of this stuff. And
You've got all the time.
yeah. The view you see on behind me here. So about 3 blocks from our house, off to the east, there's more mountains. So we have a range of mountains on the west side of us, which was when I first the first background that I had. So out off my front porch, looking to the west, they call them the Awahis, and they are, they're only about it's about 10, 15 miles maybe to the base of those hills. And then these ones here, I think, are a little further away to the east. And up on the ridge where we live, if we walk about 3 blocks to the east, there's a big, huge cemetery back there, and it's my wife and daughter standing there. So they were kind of standing, admiring the mountains, and so I said, "Hey, that looked like a fun picture to be a background for Zoom." So I took the picture of them standing there, and so we're up about a little less than 100 feet above the Boise River. So you see that there's a this is probably it's probably only about 60 or 70 feet there. So you can see a horse there just over my, let's see, that'd be my right shoulder, down on the below, and then that's mostly farmland off in that direction. So the city of Caldwell is to the west, which is that way. No, that way. Yeah, that way. City of Caldwell is kind of like all around us off in this direction, and then the mountains are the other direction. And if you go to Boise, you're right up to these guys. So if you drive down the highway 84 till you hit Boise, they're right there. You're literally in the foothills of these mountains, and it's really cool. It's great fun, because we get both sunrise and sunsets here. So at sunrise, the mountains to the west of us get lit up by the sun as it comes up about 8:30, 9 o'clock in the morning, and it just highlights them. They just jump out at you. And then in the evening, when the sun goes down, then you get the beautiful, colorful hues that fill the sky over them in the evening. And then when they're covered with snow, of course, that's just all the more colorful. So we love the environment here. It's like, wow, and Idaho is very flat for the most part, except for these kinds of things. And you've got lots of flatness, and then you've got these hills that just pop up out of it. But it's quite a bit different than the Puget Sound in terms of, because Puget Sound is nonstop hills and valleys and ridges and things, and so it's very easy to get somewhere where you can't really see that far unless you can get up high. Here you can see a long ways almost from anywhere. And there are a few places where if you're right up next to a ridge or something like that, yeah, you don't see much in that direction, but you can usually look in a different direction and then you can see for miles. And so it's a very, very different environment, but great fun. We're loving it. So, but I'm going to miss seeing you guys in person. That's for sure. I mean, I always love the in-person SRS meetings, and I'm going to, miss that. If we happen to be in town over one of the weekends, I'll be sure to pop in, of course, but don't know when or how that's going to happen. So, but my 3 sons still live in Seattle, so we'll be coming back on a fairly regular basis to see them. So
wait till summer.
Yeah.
Spring.
Yeah, in the summertime it'll get it gets very hot here in the summertime. So it's a very different different environment, but we like that too. My wife likes the heat, and so we oftentimes we will go south, so we'll head to Arizona or we'll head to Texas or places like that, and Yeah, well, in the summertime, I guess it's like, okay, so spring and fall actually are really nice times to go to those places, you know, because it's starting to get warm, or it's just kind of at the tail end of the heat. You know, you're kind of at the you go down there in the July, August time frame, and you know you get cooked. But we have friends in those places, and so it's fun to see them. And everybody's got air conditioning, so it's like, well, okay. You know, your car's got air conditioning, your house has got air conditioning. What the heck?
Way too hot. I did go to Cedar City a couple of years ago. While it was hot there in Utah, southern Utah, I got to drive up into the mountains on one day, or ride into the mountains, and it's nice and cool up there, and it almost looked just like the Northwest.
Mm-hmm. Mm-hmm.
That was there. I wouldn't have thought they had all that green trees up there. And I do know they had green trees, Flagstaff, and Oregon, Mexico. But for the most part, too hot for calling. And when you remember that 115 degree day that we had here a couple years ago? I was ready to die at work. I was like, this sucks. And I almost, I did get ill, and all I was doing was online training. You know, I wasn't going to about touch any type of machine. Way too hot. And they let us go from work 2 hours early. I went home, stayed in the cool apartment. Luckily, it was only 80 degrees or so, but I don't have air conditioning. There's no viable window to do that in except for one. My little window taker is all the way in Wyoming. For the most part, my place doesn't.
Yeah. Well, I don't know about you guys, but I haven't had lunch yet, and it's after 2 o'clock in the afternoon. So. I'm gonna grab some lunch and maybe might even head over to the local grocery store and see if I can get myself a nice just get a basic sieve to see if I can help cure my pellet stove issues here, or at least slow it down. So
Good luck with that, Steve. Thanks for hosting the meeting.
yeah, well, thank you for attending, and yeah, I'll be looking for your CES pictures there. So all right, good to see you too, Colin. Have a good one. All right.
See you guys. Bye.
Bye-bye. 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 That's Edwin, right?
Yep.
Yeah. Bye-bye, Edwin.
Bye.
Bye-bye.